Hello, and welcome to Skill-Lync. Today, we are excited to introduce you to our Introduction to Advanced CFD Analysis course, your gateway to mastering the intricacies of computational fluid dynamics and preparing for a thriving career in this cutting-edge domain. This is a certified course, so don't forget to fill out the form linked in the description after completing the session to claim your certificate. Share your achievement proudly on LinkedIn and showcase your expertise to the world. At Skill-Lync, we collaborate with industry experts to design courses that bridge the gap between academics and real-world applications. This course is packed with the practical knowledge and industry insights, equipping you with the skills required to excel as a CFD engineer. Before we dive in, make sure to subscribe to our channel for more industry-relevant courses and tutorials. Click the subscribe button and stay tuned for updates on CFD, engineering design, and much more. In the first chapter, we begin by understanding what computational fluid dynamics, or CFD, is, and its significance in the engineering world. You learn about the science of predicting fluid flow using mathematical equations and numerical methods. From solving complex fluid dynamic equations to utilizing high-performance computing, we will explain how CFD plays a vital role in design optimization and performance analysis across multiple industries. In this chapter, we explore the essential responsibilities of a CFD engineer. You will learn about tasks such as CAD geometry preparation, mesh generation, solver setup, and interpreting simulation results. We will also discuss design optimization techniques, reporting, and collaborating with cross-functional teams to deliver real-world engineering solutions. Whether you're optimizing the aerodynamics of a car or ensuring thermal management in a device, this chapter lays the groundwork for your professional role as a CFD expert. Here, we dive into the theoretical backbone of CFD, the governing principles such as the Navier-Stokes equations. We will explain how these equations represent the laws of mass, momentum, and energy conservation in fluid flow. You will also understand how these complex equations are discretized into simpler forms that CFD software can solve. Topics like boundary conditions, turbulence modeling, and steady versus unsteady flow simulations will also be covered in detail. In this chapter, we will walk you through the complete CFD workflow, starting from pre-processing tasks like geometry cleanup and mesh generation. We will move to solver setup, where you will configure numerical methods and boundary conditions. Finally, we will discuss post-processing techniques, including extracting meaningful results like velocity contours, pressure distributions, and flow separations to make informed design decisions. The fifth chapter highlights the diverse applications of CFD, from automotive and aerospace engineering to biomedical devices. You will see how CFD solves these real-world problems. Explore examples like predicting drag and lift for vehicles, optimizing underhood airflow, and simulating blood flow in medical devices. This chapter showcases how CFD contributes to innovation and efficiency across industries. This chapter introduces you to the various CFD tools commonly used in the industry. You will learn about pre-processing tools like Ansys and Hypermesh, solvers like Ansys Fluent, and post-processing tools like CFD Post. Gain an overview of how these software solutions work together to execute complex simulations. CFD isn't without its fair set of challenges. In this chapter, we discuss key issues like computational complexity, mesh independence, and validating simulation results. You will learn how to overcome these hurdles and make informed decisions during the simulation process to ensure reliable outcomes. In the final chapter, we focus on the career opportunities awaiting skilled CFD professionals. From automotive and aerospace companies to startups and research labs, the demand for CFD engineers is immense. This chapter provides insights into the diverse roles and industries where you can make an impact as a CFD expert. Thank you for joining us on this learning journey. By completing this course, you will develop a strong foundation in computational fluid dynamics and be ready to tackle real-world engineering challenges with confidence. Don't forget to subscribe to our channel for more insightful tutorials and courses. Once you complete the session, claim your certificate, share it on LinkedIn, and kickstart your career in CFD. Let's get started with Introduction to Advanced CFD Analysis, your first step toward mastering the science of fluid dynamics.
So a very good evening to all of you. So today's webinar session is about introduction to advanced CFD analysis. So the agenda of today's presentation is like we will go like this: a brief introduction to computational fluid dynamics, then responsibilities of a CFD engineer in an industry, then governing principles of computational fluid dynamics, CFD workflow, applications, softwares, and challenges, and job opportunities. So I will try to keep as much as simple. We will not go into any mathematical complications of computational fluid dynamics. So mostly the presentation will be like industry oriented, application oriented. So coming to the definition of computational fluid dynamics. So it is the science of predicting fluid flow phenomenon by solving mathematical equations using numerical methods. For what? For characterization of flow fields using high performance computing. So as you all may be knowing that the governing equations of fluid flow, that is the Navier-Stokes equations, they are actually second order nonlinear partial differential equation. And for complex problems, there are no exact solutions available for these equations. But you might have studied in your curriculum that for a simplified problems like flow through a circular pipe or flow between two fixed parallel plates using the initial and boundary condition, you can simplify the Navier-Stokes equation and you can obtain solutions for velocity profile or flow rate or pressure drop, etc. So that is like wherein there are certain problems we can simplify it and we can find the exact solutions. But in most of the cases, in reality, many of the engineering applications, including fluid flow, are complex and which cannot be simplified and solved like that. So in those scenarios, we go to numerically solving these governing equations using a computer. So basically what we do, this you might be knowing, but still I will just give a brief introduction. So we will discretize the fluid domain or the problem domain, and we approximate this partial differential equation to algebraic equations, and we solve for each of the cell in the discretized domain. So there are different discretization methods you might be aware, like finite volume methodology or finite difference methodology or finite element methodology or lattice Boltzmann method, etc., etc. So all these methodologies, what is common is that the partial differential equation, that is the Navier-Stokes equation, that is approximated as an algebraic equation, and it solves numerically. It is an iterative process using a high performance computing. Okay, so why do we do this basically? Because we need to, what is our objective of doing this? So we need to predict velocities, pressures, shear stress, forces, temperatures, etc. And why we require this? Because we want to ultimately optimize the design of the product, or we need a better design of any better design, or we need a better performance, or we need a better fuel economy, or we need a less drag, or we need to predict the heat transfer in a boiler, or heat transfer of a hot fluid flowing through a pipe, or we need to optimize the piping network. So these are various applications that we will see in the coming slides. So that is the overall objective and introduction to computational fluid dynamics. Okay, so now coming to the responsibilities of a CFD engineer in an industry. So that is like, say, in any company, like there will be a CFD team, and the CFD engineer will be a part of this team. And based on his experience, he may be taking care of multiple projects or a single project or part of some project. But anywhere, for an entry-level professional, these are some of the basic roles and responsibilities. That is, first and foremost is study of the input CAD geometry and pre-processing it. So when I say the study of input CAD geometry, he should be aware of what problem he is going to solve. Then he should know the real application of that particular problem. Then he has to modify the CAD geometry or clean up the CAD geometry to meet the requirements of CFD solutions. And that includes CAD cleanup. Then he needs to do the meshing, then solver setup, etc., etc. Then he should have a thorough understanding of the fluid flow physics. That is actually essential for setting up of the problem with proper numerical methods, flow, the type of flow, the boundary conditions, the turbulence models, the convergence criteria, etc., etc. Then obviously after solving, computer will do the solving part of it, so the individual don't have to actually worry about it. Then after the solution, actually the important part comes the interpretation and meaningful conclusion of the CFD results. Then obviously report generation. And once the results are analyzed, he may need to suggest the design modifications based on his results. Then in certain kind of problems, he may be dealing with achieving certain design targets, like optimizing the pressure drop in a pipe, or optimizing the flow distribution, or optimizing the drag coefficient, lift coefficient, such things. So in those scenarios, he might have to do a lot of design optimization studies to achieve those targets. Then obviously the teams work in as a collaborative environment, so different teams will be interacting with the CFD teams. So they have to hold on discussions with cross-functional teams to convey the results and design modifications, etc. And to a senior level or senior member in the team, they will be attending project meetings to understand the cost, quality, and target specifications of the product. So these are the core responsibilities of anyone who would be a part of CFD team in any industry. So now coming to the governing principles of CFD. So basically it all starts with governing equations. So so you all know what is a governing equations of fluid flow, Navier-Stokes equation, and how it comes, what it represents is any governing equations of any phenomenon is the mathematical representation of that particular phenomenon. So the physical phenomenon we convert into a mathematical equations, so that we can obtain solutions for that phenomenon or characterization of that phenomenon. So we have, like in Navier-Stokes equation, we have momentum equations, x, y, z momentum equation, and there is a continuity equation. So we have mass conservation and momentum conservation, and wherever the heat transfer is involved, we couple these momentum equations to energy equations. Otherwise, if heat transfer is not involved, it is just we are solving the momentum equation plus mass conservation equation, that is well-known continuity equation. So we have the governing equations now in mathematical representation. Now what we have to do is, we have our problem domain, and we are approximating this partial differential equation to algebraic equation. So that is the mathematical side of it, but that anyhow software will do. But what we have is, we have the CAD geometry in front of us, and we all have to do finite volume discretization. Meaning finite volume discretization is nothing but whatever the domain you have, that you have to divide it into cells and mesh in simple terms. And for each cells in the domain, these algebraic equations are solved, and you will be finding the flow parameter of interest, whether it is velocity, pressure, density, or whatever it may be. So that is the spatial discretization. And another part is temporal discretization, because the flow may be steady or unsteady, depending upon the problem and assumptions. Sometimes we approximate the unsteady problems are steady state. Actually, all the flow problems are unsteady, but we, with certain reasonable approximations, we could able to find average quantities by approximating it as a steady state problem. So in those scenarios, we have the temporal discretization, that is discretization in time. So there are different schemes available in the CFD solver. It's called explicit schemes and implicit schemes. Explicit schemes are those in which, if you are so I said before, this is an iterative process. So if at a particular time step, if you want to calculate the flow parameters, then in an explicit scheme, you would be knowing the previous time step values, and that would be used to calculate the current time step values. So that is called explicit time marching. Whereas in implicit schemes, you would not be knowing the previous time step values and current time step values, and you will end up with a set of equations in the form of Ax is equal to b. It's a system of linear equations, and you solve all these equations simultaneously using certain numerical schemes. So those are called implicit schemes. Okay. Anyhow, like since in industry people use commercial codes, so they don't have to actually worry about this. These are the things which happens in the background of the solver. They have to select the right schemes based on the flow problems. Okay. And so spatial discretization over, temporal discretization is over. Now coming to the flow type, as we all know, like most of the engineering problems or flow problems are turbulent flows. Only very few cases where the flow is quite orderly flow, wherein we call it as a laminar flow. But most likely it will be turbulent flow. Then there are certain turbulence models are there to model this kind of turbulence flow, which we will see in detail in the coming slides. And another last but not least is the setting up of the boundary condition. Why it is important is, so as I said before, we are approximating a real problem into a numerical solution. So we need to know the actual boundaries of the problem so that we can specify. So what is at the for our computational fluid domain, we can specify the boundary, which will be the representation of the actual values in case of the actual problem. So there are different boundary conditions like inlet boundary condition. So inlet boundary condition, it could be a velocity inlet or pressure inlet or mass flow inlet. So depending upon the problem, we have to arrive at the right boundary conditions. So these are the governing principles of any CFD application, whether it could be FDM, FPM, LBM, whatever it may be. So mostly these things are like which is already coded and inbuilt in the commercial solver. So we just have to pick the right options and run the solution. So that knowledge we require, but the coding part, that is not the scope of this webinar. So that is altogether a different field. Now coming to the CFD workflow. So this is what, like from a user perspective of a CFD software or an industrial application, like most of them will be working with. So the first part will be pre-processing, second part will be solver setting and solver calculations, and the last part will be post-processing. The pre-processing involves, so from the designer, one may receive the geometry, then he may need to know what needs to be required for his CFD problem. Those domains he has to extract, clean up other things. Then he has to extract the fluid volume. He has to define this inlet, outlet, or other boundaries. He has to generate surface mesh. He has to generate volume mesh. Then the quality has to be cleared for both surface mesh and volume mesh based on the type of the mesh. Then after that, the solver settings part will come. So in that, he has to select the right flow models, whether it is laminar, turbulent, and fluid, define the fluid properties, then numerical methods, boundary conditions, convergence criteria, the parameters which he needs to monitor for the convergence, etc. And obviously running the solution. Then comes the post-processing part. So that is the of parameters which is of interest. So it could be velocity vectors, velocity contours, streamlines, flow recirculations, flow separations, or it could be forces, drag, lift, or it may be the heat transfer coefficient, or it could be the temperature distribution. So depending upon the application, the person or CFD engineer can extract his parameters of interest, and accordingly he can move forward with design modifications or optimization, whatever, based on his objectives. Okay, so we have understood a general workflow. So we have got we got some geometry, we did some processing, and we ran the solution, and we got some results. Then how do we confirm that, okay, I have got a consistent, accurate results? How do we confirm that? So that is actually a very challenging and tricky part of this CFD simulation. So whatever we run, we get some colorful results, but sometimes it may not make meaningful conclusions. So in those scenarios, actually we have to so there is a concept called mesh independence. So our solution, whatever the solutions we obtain, it should be actually independent of the mesh. So here, as you can see, this is the geometry. Okay, so this is a straight pipe that convergence, and then there is a straight constructed portion, and there is a sudden expansion. So here you can see M1, M2, M3, M4. Now the only difference in M1, M2, M3, M4, as you see, is the total number of elements in this domain. So M1 has got, say, 6.3 lakhs elements, M2 8 lakhs, M3 1.2 million, and M4 3.1 million. Okay, so these four has got different elements in the increasing order of number of elements. Okay, and as you see in this problem here, there is a red line. So this is the center line of this problem, and along this center line, the velocity is plotted, as you can see in the graph. So there are four curves you can see, right? One is orange, blue, then one is yellow, blue, orange, and another shade of blue. So what is that one thing you can observe here is, see, all the velocities, I mean, for all the four meshes, you are not seeing a consistent velocity pattern. So you see the difference here, you see the difference here, you see the difference here. So for each mesh, we are getting a different velocity profile along the center line. Actually, this should not be happen. Actually, whatever the mesh, your result should not change with mesh. You have to get a consistent velocity for all kind of mesh. So I just want to show the difference. That is why I have put a different meshes so that you would observe the differences in the velocity along the center line. But when you start doing it, you have to actually get this profile. Like if you are comparing 2 or 3 meshes, you should get the same velocity profile for all the meshes. So accordingly, you should choose that mesh for the studies. So that is one thing. Like every CFD engineer should aware, and you should confirm before starting with any big project. So now that is one part. Now second part is like how do we ensure that, okay, we have ran a CFD simulation and we have got a results, but how do we make sure, okay, I have got, or I have modeled almost close to the real world problem, and what is and my accuracy is almost 100%. How do we ensure that? So that is actually one of the challenging task of any CFD simulation. Not only CFD, any computational methodology, whether it is FEM or a CFD. So one has to actually make sure that he or she is modeling the real world phenomenon as close as possible. So there are limitations. One cannot achieve 100% of real world problems, because that may require extensive computational power, and it is highly expensive. But then we have to make sure our errors are within the acceptable limits. So there comes the two terms, that is verification and validation. So verification is nothing but, if we go as per the definition, it refers to the accuracy of your numerical solution. So that is actually dependent on what your mesh, how good you have designed the mesh, your spatial and temporal discretization accuracy, your numerical methods, your higher order schemes, etc., etc. So where were we? Yeah, verification. So verification actually refers to the accuracy of the numerical solution of the governing equation. So that is, if you see, so here the parameters which we giving, that is in the mathematical model, that is mesh, then numerical methods, schemes, all those will dictate the accuracy of the numerical solution. And then the validation is whether the simulation is an accurate representation of the real world that is being modeled. So if you see here, I hope everyone can see my cursor. So this is the actual experiment or the actual reality fluid problem. So that is the actual one. And we, with certain modeling assumptions, we are taking the simulation model. And with certain assumptions, we are actually putting the fluid properties and other inputs. And there are certain approximations and error in the numerical solution because we are actually approximating it as a algebraic equation. There may be some round off errors and truncation errors, etc. And finally, we are obtaining a simulation results. And this is from reality. If we do some experiments, we get an experimental data. It also got some experimental errors. And if we compare the results of simulation and the experimental, then we get some error margin that is called E. So that margin should be within the acceptable limits. So sometimes if you compare the simulation and the experimental results, you may get 80% close to the experimental results, or sometimes 85% close, or 95% close, or 98%. So you need to always have to quantify what is the error margin you are having with the actual results, so that you will have always that confidence. Okay, I am predicting, okay, with 5% error or 10% error. So that will give you a confidence, and you can actually confident in the process you are using. Otherwise, we will be always in a dilemma. Okay, I have got some colorful results. I don't know how far it is true. So that confusions can be avoided. So these two are the important aspects of any CFD simulation. Okay. So that is all about getting a CFD simulation and how we are making sure it is accurate and the real problems are being captured to the maximum possible extent. We will touch upon an introduction to the turbulence models, because whenever one goes start solving an industrial fluid flow problems, the fluid flow will always be turbulent, and turbulence modeling is altogether a vast topic, and it itself is a big topic, and it is taught as a one full paper in the course curriculum. During MTech and all, but with this short time, we will see how far at least the practical side of what turbulence models need to be used at what situations. So those things we will see. So the turbulence is an unsteady phenomenon where the flow is highly irregular. It will be fluctuating both in space and time. It is highly rotational, and there are large and small scale fluctuating eddies as shown here. So you can see, say this is a flat plate. If incoming flow is coming with a free stream velocity of u infinity, and at the starting you can see the flow is laminar, and as and when it encounters friction and flow rate increases, it starts transitions to turbulent, and in the fully turbulent region you can see the turbulent eddies, which is of rotating nature, and there are small scale eddies and large scale eddies. So capturing these small scale and large scale eddies, that is the actual challenge of turbulent flow. So then we have a turbulent boundary layer profile. All of you might have studied that in your BTech and MTech courses. So basically there is a region very near to the wall, near wall region, which is called viscous sublayer, and above that there is a layer called buffer layer, and top of that there is a region called log low region. So you can see here at the wall, as you all know, the fluid velocity will be 0, and there is a region where the velocity of the flow is linear to the distance from the wall, and the dominant stresses in this particular region is due to wall shear or due to viscosity. So that is called viscous sublayer. And the buffer layer, the stresses are dominant due to turbulence. Those are turbulent stresses. And in the log low region, the flow is fully turbulent. And so when solving for turbulence, our challenge is to what extent one need to capture. So based on the problem, one has to take a call. Okay, do I need to exactly capture till log low region, or full physics, all the boundary layer regions of turbulent model? So that is what it is being addressed using turbulence modeling. Okay, so the turbulence modeling, usually the commercial softwares available in the market, be it Fluent or STAR-CCM or whatever. So all those are RANS models. So RANS is nothing but Reynolds averaged Navier-Stokes equations, which are used to compute the flow field. So we have discussed Navier-Stokes equation, and we can, from Navier-Stokes equation, we can arrive Reynolds average Navier-Stokes equation by using, there is a methodology called velocity decomposition, where the velocity is decomposed into a transient and an average component, and that, so the mathematical derivations are long. So but the crux is like the UVW velocities are decomposed into a fluctuating component and averaging component, and that will be plugged into the Navier-Stokes equation, which results into an additional term called Reynolds stresses. And to model that Reynolds stresses, there are certain approaches had come, and those are called turbulence models. So for modeling the turbulence, and for with this additional equation of Reynolds stresses, these turbulence models have come. So there are different turbulence models like K epsilon, K omega, etc., etc. But the whole objective is how the whole objective of all these exercises is how to capture this turbulent boundary layer regions. And this is near wall phenomenon. And in near wall phenomenon, the gradients, velocity or shear stress, all these will be, there will be higher gradients. So, and so that is the objective of this turbulence modeling. And okay, and RANS is one of the best approach for in many industrial applications because of its computational efficiency. Why? Because if you see here, the viscous layer and buffer layer are small regions near the wall, which cannot, most of the cases, which is not resolved using a computational mesh. So these two regions are resolved using a wall function approach. So wall function is nothing but an empirical approach wherein it obeys the physics near the wall, so that we can calculate the flow parameters over that region, and we just need computational mesh only to capture the log low region. So that is the whole objective of the RANS approach. Now we will come individually to each and every turbulence models and applications of that. Then we will see some more other aspects of turbulence modeling like Y plus and all. So the most famous and commonly used turbulence model in any industrial application is K epsilon model. So the K stands for turbulent kinetic energy, and epsilon stands for the rate of dissipation of turbulent kinetic energy. And when we, so what this model does is, so this model will not simulate the flow in the buffer layer and viscous sublayer. So it just captures the flow in the log flow region. And to capture the physics in the buffer layer and viscous layer, we use the wall functions. Okay. And for this model, the Y plus values are between 30 and 300. I will come to Y plus once I explain all the turbulence model. For time being, let us keep, okay, our Y plus we require between 30 and 300. Let us keep it like that. Okay. And this model is best suited for external flow applications around complex geometry. So when I say external flow applications, basically it is well suited for bluff bodies. That is bluff body, when I say like flow past a cylinder, flow past a sphere, or flow around a car, or flow around a truck. For those kind of applications, K epsilon model is one of the best model. And it is not suitable for flows encounter adverse pressure gradients and strong curvature in the flow. Like these models are not suitable for where there is an adverse pressure gradient, or if there is a pipe with a lot of bends. Then it's an example. So where these models, K epsilon model will not be a good choice for modeling those kind of things, those kind of flow applications. Okay. And this is another famous model, K omega model. So where K is the turbulent kinetic energy and omega is the specific rate of dissipation of turbulent kinetic energy. And it is otherwise called a low Reynolds number model. And here we try to capture the viscous layer and buffer layer. with the computational mesh, and we require y plus value approximately close to 1. Okay. And sometimes it can be used along with val functions also. There is no harm in that. So in those scenarios, we will not. So we can go for a slightly higher y plus around 10 or 15, and then the val functions we capture the near val phenomenon with we bridge with the log-law region. And this model is actually best suited for internal flows and flows that exhibit strong curvature, etc. So best example for this model is like flow through a pipe bend. So those are the applications where we can use K omega model. So in this model, one factor which we need to take care is like our mesh should be very denser to the wall. So our y plus should be close to 1. Accordingly, we need to place the first cell height. So those concepts we will discuss when we go for y plus discussion. And this is another famous model, SST K omega model, shear stress transport K omega model. So this is actually a combination of the first two models we have seen, that is K epsilon and K omega. And here also we require y plus up close to 1. But here one advantage with this model is it automatically switches between K omega and K epsilon. So in the near wall where the velocities are less, the model switches to K omega and it works. And in the free stream or away from the wall where the flow velocity increases or the turbulence increases, it switches to K epsilon. So this is actually a very good model for a prediction of flow separation and reattachment. And denser mesh is required near the wall and free stream. And this model is well suited for the problems like in the pump, centrifugal pumps, or even external aerodynamics. There are some, with some modifications, this model can be used. So these are the applications of SST K omega model. So these three are the common, most common used turbulence model. There are some other models also, but I'm just touching upon the most commonly used turbulence model. Yeah. There are other two approaches of turbulence modeling. And so till now what we have seen is RANS approach, Reynolds average and Navier-Stokes equation, where we are actually interested in the average quantity. So we average the Reynolds Navier-Stokes equation, and we using the turbulence model we find the Reynolds stresses. Now the another method is direct numerical solution, or it is famously called DNS. Here actually there is no averaging, nothing. This fluctuating components directly we plug into Navier-Stokes equation, and we try to resolve all the eddies with mesh, be it a large eddy, be it a small eddy. We try to resolve all the problem. We try to resolve the domain with the computational mesh. Then we need to go very finer mesh near the wall to capture the smaller eddies in the near the wall, and it becomes computationally very much intensive, and it is computationally very much expensive. So it is not suitable for industrial applications. Okay, for academic interest, one can actually explore, but yeah, so that is what this direct numerical simulations. And another one is large eddy simulations, where it is a kind of industrial plus academic, but still it requires a lot of computational power. So in LES simulations, we resolve some of the eddies with a mesh. So you can see two pictures here. One is written here bad LES, and one is written here good LES. So what is the difference? You can see the left side we have a bigger eddy. Then moving towards right, we have smaller eddy. Then moving towards right, we have very smaller eddies. But if you see the good LES, yeah, our area under the curve actually extending towards more smaller eddies. So this is a good LES. But the top one, it is just stopping here. So it is only capturing the eddies with this size. But here it is furthermore capturing eddies with smaller size. So this is always there is a trade-off between the computational power we have and what we need to capture. So accordingly, one has to decide what is the size of cutoff size of the eddies they need to resolve. And there are some other mathematical models also. So that is beyond the scope of this, how they can specify the cutoff size for large eddy simulations. Okay, so these are the overall brief about the turbulence modeling. So now coming to the y plus. So I told like for K epsilon we need y plus between 30 and 300. K omega it should be close to 1. So what is this y plus? So this is a non-dimensional wall distance which is used to place the first layer near the wall. So using the y plus, we will calculate the first layer of mesh where has to be placed in our problem. Okay, at what distance from the wall. So suppose if you are using a turbulence model, K epsilon, and we know that y plus should be between 30 and 300. So we are going to do meshing. We need to calculate our first layer height. So we could actually put in y plus, we know 30, and y is what we need to calculate, the absolute distance from the wall. And mu tau is the frictional velocities, which is given by the square root of a wall shear stress by density of the fluid. So in most scenarios, we will not be knowing the actual wall shear stress. Okay, but for say simple problems, say flow over a flat plate and all, we know the formula for wall shear stress. It is CF by half rho u square, and CF is given by some empirical correlation 0.0064 root of REX or something. So in those scenarios, we can actually calculate the wall shear stress and density. We know density of the fluid, and you can actually find the first cell height, absolute distance from the wall, and based accordingly you can grow your prism layers and put the first cell height, and then accordingly you can grow how many layers you want. So that is one way of doing it. Suppose if you are not able to calculate the wall shear stress, suppose if you are, say this is your geometry and you want to put first layer height, so then you don't know the wall shear stress, but still we can either go with the flat plate approximation, initial guess, calculate the wall shear stress and calculate the y plus value, distance, absolute distance from the wall, then grow the prism layers, run the simulation. After the simulation, go and plot y plus, cross check your y plus is between 30 and 300. Make sure, okay, if not, suppose if it is going below some areas where it is coming to 1 or 2, or some areas it is going above 300, then rework on the mesh on those areas, then again run the simulation, and you can correct the y plus. So that is the significance of y plus. So it gives an idea of placing the first layer height based on the turbulence model you are going to use it. Okay. Yeah. Now we will come to the application part of advanced CFD or CFD. It becomes advanced as and we progress towards the complex problems. So here, suppose if you take, so mainly I'm concentrating on 3 domains. There are n number of domains where the CFD finds application, but I am restricting myself to automotive, aerospace, and biomedical. Okay, there are oil and gas, or then other areas like heating and ventilation, turbo machineries. A lot of areas are there, but just I'm restricting to these. Yeah. So in automotive, like the applications are like first and foremost is like the drag and lift predictions of the vehicle you are designing, be it a truck or be it a car, bus, whatever it may be. So that is first application. And second is the underhood and underbody thermal management of a car, bus, or truck. So you have a lot of plastic components and rubber hoses on your engine bay, and sensors, etc., and on the underbody also. Then you have hot parts running on your placed on your underhood and underbay, like exhaust system, manifold, engine, and there is all the neighboring components have a risk of catching fire at certain vehicle operating conditions. Then so you need to simulate it. You need to find the temperature or maximum temperature each component experience in the vehicle. If it is going beyond its design temperature, you need to work on how to protect it. Another is cooling airflow. So you all might have seen certain openings on the front of the car. So those are the openings provide to cool the heat rejected by the engine through the radiator into the engine bay. So those heat will be carried out by this airflow. So one may have to work on optimizing the airflow requirements based on the heat rejections. Another is, as you can see here, like this is a cabin, inside cabin of a car. We switch on the AC, we get nice cool air. But CFD engineer who is working on this problem, he has to make sure that, okay, the moment I switch on AC or the moment the passenger switch on AC, the cabin has to be cooled within a fraction of seconds, 1 second, 2 seconds. So that he has to make sure. Okay, the air reaches all the passengers, be it in the front row, second row, third row, with sufficient velocity. So then, so all those things he has to take care. The CFD engineer who is working on the cabin airflow. Then obviously this air comes through a duct, so and it is blown by a blower. So he has to optimize the pressure drop in the duct so that he can improve his blower performance. Then obviously there is a vent through which the air expands to the cabin. So the vent shape also he has to design so that the vent makes sure the air to flow maximum expanded to all directions. So those are some critical areas wherein a CFD engineer working in automotive application has to think on and focus. And there are other like air intake system and exhaust system. Those are system level components wherein one have to work for the air intake system pressure drop optimization or flow uniformity index, or exhaust system temperature predictions due to hot gases flowing inside through it. So these are the applications related to automotive. Now coming to aerospace, again, it is a vast field. It is not just limited to what I put 5 or 10 applications on my slide. And it is not as simple as, no, even the other one is also not simple. Yeah, so these are very complex applications where the prediction of drag and lift, again, the cabin comfort inside the aircraft, airflow inside the aircraft cabin for the passenger comfort, aerofoil designs, that is the most crucial part of it, the lift and stall, all those aspects. Then another aspect is supersonic missiles. Missiles, because countries make missiles, and what is their main objective is maximum range. It has to travel 5,000, 10,000, or it has to reach 2-3 countries beyond. If they are able to hit, they will be happy. So that range. So again, that also CFD has to play a major role in that. And hypersonic launch vehicles, as you know, like the space vehicles, re-entry vehicles. Actually, that is a very complex phenomenon where you will have this. I'll just mention how complex it is. Like, so it is actually a compressible flow. Then you will have a shock layer at the front of the space vehicle. Then there is a boundary layer, and this boundary layer is a bigger boundary layer than incompressible flow boundary layer. And there is a phenomenon called boundary layer heating take place, which is not there in the incompressible flow. And there is an interaction between the shock which is formed in front of the launch vehicle and this boundary layer that will create a altogether different form of physics, and the vehicle will experience different atmospheric conditions as it travels from Earth to space. Some regions the vehicle will experience the ionization of gases, some regions it will be like inert gases. So then now you can imagine somebody is doing the CFD analysis of this, how much physics they need to solve. They need to solve the ionization problem in the atmosphere, they need to solve the shock problem, they need to solve for the boundary layer heating and prediction, and the interaction between shock wave and boundary layer. So that is like very complex things. Again, the propulsion system design, again these fans and propellers, then the gas turbine and the noise of these fans and propellers, flow induced noise. So all these are the applications of aerospace. Now, so another area of application is biomedical devices. So you might have heard, I don't know, in your curriculum, you might not be studying about all this. You might have heard a lot about automotive and aerospace, but there are medical devices which will save the human lives. Say suppose the human heart is not working. There is a device called blood pump, which can actually substitute for the heart. Then there are stents, there are heart valves, artificial heart valves. Suppose somebody's heart valve is not working, there are heart valves which can be implanted. So though all the design and development of these applications, a lot of CFD is involved. Again, here the complication is we say in automotive application we have seen one version of air, that is incompressible form of air, and in aerospace we have seen another form of air which is a compressible part of air. But here the fluid is blood, and blood is actually a suspension of white blood cells, red blood cells, all those mixtures. And that creates a very big challenge for the design of these kind of devices. So those are the applications, and prediction of aneurysms. So somebody will have a cerebral aneurysm. Also, aneurysm is nothing but suppose we have a blood vessel, and over a period of time there will be a bulging, as you can see in this figure. This is the straight blood vessel, but due to certain chronic conditions or as age progress, this straight blood vessel become like this bulge, and once it start bulging, at any point it can break, and it can mortality can happen to that particular person. So there are models using CFD. One can predict these aneurysms, and suppose if there is an aneurysm, people put stent over there, as you can see there, but then where to put the stent, how the stent has to be designed, and what is the shear force coming in that, what is the flow circulation in that area. For all this we have to do a lot of CFD based optimization. So these are some of the application part of it. Okay, so we have seen applications, we have seen little bit of theory, turbulence modeling, etc., etc. Having said all this, usually the commercial softwares have made the life of CFD engineer very easy. So once we have a software, we don't have to think much. Everything is there in the GUI. We just need to know what options want, click it, execute it. So as I mentioned before, our workflow is pre-processing, solver setup, and post-processing. Not all the softwares are listed here. These are the few commonly and most commonly and famous softwares which is used in the industry. Pre-processing, ANSA, Hypermesh, Power Delta, Ansys Meshing, ICM CFD, and solver, Ansys Fluent, STAR-CCM+, AcroSolve, PowerFlow, XFlow, and post-processing, Power Insight, CFD Post, and Ansys Insight. Yeah, and challenges. Yeah, already I have mentioned in some of the slides the challenges for a CFD process and CFD engineer. So I will repeat it. So we always make assumptions and approximations in order to simplify the problem. That is the biggest challenge for us, because we need to know how much we have to assume and how much we have to approximate. So that is a judgment based on your problem, your experience, and the type of results you want. So that is always a challenge. And always you need to have a really good mesh to capture the complex flow features. And sometimes it leads to the limitations on your computational capability you have. So then you need to take a call what accuracy you need based on your computational capability or computational HPCs you have. Yeah, and sometimes nowadays a lot of aberrations are coming, different turbulence model, different valve functions, different numerical schemes. So then you may be finding, you might be trying to solve a complex phenomenon, and you might be using some complex schemes. Then you will end up with a convergence issue. Then you may need to fine tune the model and get it right. So choosing those parameters, those are also certain aspects of challenges. Then turbulence, as I said, it can always be modeled with approximations. So it is not going to be always 100% we are going to capture the turbulence. So that is also a challenge. Then, okay, computational power, as we already discussed. And the most important is the CFD results are always need to be validated with experimental flow visualization results, and you need to quantify the error which you are having with your experiments. So that is important thing. Yeah, now this is, I think, final slide. Job opportunities. So just don't go with the slide. I have put only very few numbers, and just automotive and aerospace and some engineering service companies, but there are lot of applications, even drug delivery to the or drug mixing, or as I said, the surgical planning. Those are n number of applications, but these are the common, those are specialized things. But the common a CFD analyst or engineer can find job like in automotive, aerospace, and engineering service companies, like these famous companies I have put, like TCS, HCL, Infosys, Satyam, Minjo, Tata Elxsi, all have CFD teams, and they all undertake projects which we have come across in our previous slides. And if you see the OEMs, Tata Motors, Mahindra, Valeo, Dassault System, Boeing, Airbus, Post Motors, Ford, still a lot of companies are there. Yeah, then new startups, like there are nowadays lot of new startups are coming up for electric vehicle development, electric helicopter, a lot of things are coming. So there also find lot of opportunities. And obviously, like in the premier institutions like IITs and IAC or other various government laboratories, you will find CFD research applications, where you will not be doing with sometimes commercial solvers, but you will be working on certain development of certain schemes or certain turbulence model expansion, or some certain validation of certain problems, or certain solver developments, or addition to the server developments. Those are where you will find the research opportunities also. And I think yeah, by this I'm ending. The presentation is over, and thank you for listening. And I don't know how much time I have took. Hope I have done it in the as per the schedule. Yeah, thank you.